Okay, let's do it. Probability review. So, last we did was the question 1 of the extended response section, went through that whole sequence. Now we're going to move on to question 2, unless of course there's anything specific you or anyone else would like to focus on. Seems about right to continue practicing that skill of being able to identify what probability type is being asked about, and then being able to, answer the question based off of what probability type is, chopping and changing through the sequence of questions. Now, okay, we do have someone new joining us, so we'll just quickly take a moment to introduce the setup that we have. There's going to be at least 2 main cameras that you want to have a look at. One is within the actual Zoom meeting itself. If you tap through, you'll see a camera that's pointed at my CAS calculator. You'll probably want to pin that by right-clicking and selecting pin. That way you can immediately chop and change between that, where we'll be using CAS-related stuff, and the screen share, which you'll see at the top of the meeting menu. You'll see meeting and screen. If you have any issues checking through any of those, let me know. Happy to work through any technical issues. But otherwise, okay, probability. Let's crack on with it. We've done all the content, so we're pretty much just going through now and doing all of the extended response questions so you can practice knowing when to use what. Starting with question 2 here. Electronic sensors of a certain type fail when they become too hot. The temperature is modeled as a normal random variable with a mean of 95, standard deviation of 5. So it's fairly obvious off rip, this is going to be a normal distribution question. If the probability of t less than a is equal to 0.8, find a to 1 decimal place. Does anyone remember how we do these kinds of questions when it came to normal distribution? I think you came off. Oh, there we go.
Yeah, so is it the integral from wait,
Integral can work.
wait,
It can work. It's not the suggested way of going about it, but you can keep going, yeah.
shouldn't there be a lower and upper bound? Or
Yeah, so what do we know about the normal distribution? If I pull up the normal distribution, it itself is a probability density function, and so yeah, you absolutely could be using integrals to solve this, so long as you remember what the equation of it is. I'll just pull that up now.
do we need the normal distribution formula for this?
Not necessary, but if you're going to use integrals, you do need it, yeah. You would need to put your mean and standard deviation in those spots, put that in your CAS, and then you'd be evaluating from, since a is your upper bound here, you'd put a as the upper and negative infinity as your lower. CAS solve for it to be equal to 0.8. That will work. Better way of going about it, because the CAS has inbuilt functions for the normal distribution, you're better off using, at least in this case, the inverse normal. Because what you're trying to do is solve an upper or a lower bound. Inverse normal, all you're going to do is plug the information directly into this and you'll get the right answer. But exactly as you suggested, that will work. If you put the mean and standard deviation in those spots on your f of x and use the continuous probability approach, it'll get there. And what you'll find, oddly enough, is that like the last 3 decimal places at the very end will be slightly different, and something about that implies to me that whatever they're doing to make it faster in the CAS is more approximating the normal distribution rather than doing it exactly. But you don't need to worry about that because it's like, in the 9th or 10th decimal place all the way at the back end. You don't have to worry about that. Now, the thing about inverse normal, we have to make sure that whatever we put in as the area is pointing left. So if this is probability of t less than a, if I draw a quick diagram on the other camera, and turn up the brightness so we can actually see it. There we go. Okay, so drawing up our normal distribution, our bell curve, probability of t less than a is 0.8. So you're going to have some mean in the middle, which we do already know. We have an a value, and everything left of that, because it's less than, is equal to 0.8. You could fill this out more by putting the mean specifically as 95 if you wanted to, but all we're really doing here is making sure that we know what direction the probability is pointing. And for our TI Inspire CAS, it needs to be pointing left, which it already was. So 0.8, mean of 95, standard deviation of 5. That will get us the value of 99.2. We wanted to get to 1 decimal place there. Just for the fun of it, I'll see, hopefully the CAS doesn't brick itself trying to do an integrals approach, but let's see if we can do it this way as well, just as a proof of concept. And while I'm typing this up, if you have any questions about the faster way of going about it, let me know. Hop off mute or even pop it in the chat, either way. Root 2 pi e to the minus half times all of this squared, x minus the mean of 95, standard deviation was 5, dx is equal to 0.8, comma a. And let's just pray the CAS doesn't brick. Worst case scenario, I can just hit the reset button and it'll get there eventually. Cool. Alright, that'll spend some time cooking. Once that's ready, we'll see it. If it still cooks forever, then I'll just reset my CAS and we'll continue on from there. But with any luck, it'll fix itself out relatively quickly and we'll see that it'll come out to be 99.2-ish. And those last couple of decimal places at the back end might be a little bit off. But okay, cool. So the main way of going about that, clearly, is going to be doing the inverse normal. Was there any questions around that one?
How do we do it on normal CAS?
How do we do on what CAS, sorry?
Yeah, the other CAS, Casio.
Other CAS, Casio? Yeah. I think the battery on my other CAS, the Casio, is gone. Let me pull up. I think I might have written it down here. There will be an inverse normal for the Casio. The only thing that you'll see a bit different will be there's a tail setting for left, right, or center. You're just going to select left. Otherwise, everything else should be the same. Mean, standard deviation, and it's only the, yeah. I think that's what you see. Yeah, can you see it on yours? Yeah, hit the left option there and you should get the same value as me. That worked?
I think, yeah, it worked.
Sweet, awesome. Yeah, syntaxes are going to be quite similar. And yeah, just to highlight, because the CAS did fix itself out now, if you have a look at those last little bit at the end, 1673, 1679. So ever so slightly different depending on which way you go about it. Obviously they're not going to make you go to that far decimal places. I just thought it was interesting to mention. But okay, part B. Find the probability correct to 3 decimal places that the temperature at which the sensor fails is less than 112 degrees, given that it was still working at 108 degrees. That is a very specific wording. Does that remind anyone of anything in particular?
Conditional.
Conditional probability, precisely. Keyword given that means that the condition that we're applying to it is that the device was still working at 108 degrees. So now that we know it's a conditional probability thing, we're going to start by writing out our conditional probability formula. This is where a bit of reading comprehension is going to come into play, because we need to know the difference between what does working mean and what does not working mean in the context of the temperature causing the sensor to fail. So let's have a read again. Electronic sensors of a certain type fail when they become too hot. T is the temperature at which it will fail. So from that point onwards, which would mean T and to the right, would be considered a fail. So if we're saying that it's still working at 108 degrees Celsius, it means that everything right of that, because the t value, or the value along the x-axis, is when it fails. So if it's still working at 108, then it means that it's got to go further right on the distribution, because it's saying it fails when it becomes too hot, right? Not when it becomes too cold, for instance. So that means the condition, given that it's still working at 108 degrees, we're saying that the conditional part of the conditional probability, PR something given something else, we now have t greater than 108 degrees. This is where they can become a bit tricky. So that's the conditional part, because that's what was given that it was still working. And then the probability is that the temperature at which the sensor fails is less than 112. That's a bit more obvious. It's telling you less than 112. So that's not too bad. T less than 112. And you can even then do a quick, it's not really a sanity check because it could work both ways, but just considering the, the range of options here, T greater than 108, T less than 112. You're looking at between 112 and 108. That doesn't actually necessarily prove that you've got it the right way around, because they do sometimes do conditional probabilities that have no actual impact on the intersection portion, but oftentimes they do. I just realized I'm very zoomed out, so I probably should zoom in and write that a bit smaller so we can see it all on the same screen. So it was probability T less than 112 given T greater than 108. Whoops. 108. And we're just going to expand that out with the actual conditional probability formula itself, which is the intersection of the two things. So 112 intersect 108. Should probably do the greater than and less than signs. I'm just being lazy. T less than 112 intersecting T greater than 108, and then to finish it off, dividing by the conditional itself, which is T greater than 108. This is how we start off every conditional probability formula question, any conditional probability question rather, whether it's continuous, whether it's normal, whether it's whatever. The only thing that changes is how we actually solve those, numerator or denominator. The denominator is going to be the easiest part of that. It's just probability of being greater than 108. And so how do we do that normal distribution wise? Get this brighter. So we're just looking to do probability of a normal distribution variable being greater than 108. Okay, well, we do know that it's normal distribution, which means on our CAS there's technically 3 options, but really there's only 2, because we pretty much will never use the normal PDF. So it's either going to be normal CDF or inverse normal. We know that inverse normal gives us x values, it gives us stuff along the x-axis, so the only other option that we could use here is going to be the normal CDF. CDF always gives you a probability over a range of outcomes. So if it's going to be greater than 108, our lower bound is going to be 108. The upper bound is going to shoot to infinity, as per standard by the normal distribution. And once again, we're plugging in the exact same mean and standard deviation. If you have the other CAS, the syntax of it, I believe, should be perfectly identical, but I think they change the order of it ever so slightly. I think the Casio flips the mean and standard deviation on top of each other. But either way, should be the same. Just let me know if you're seeing something different, and I'll fix it up.
Where do you find the normal CDF?
So it should be near the way you got to inverse normal. You would have clicked inverses. I think in the same tab where you click inverses, there should be distributions.
Yeah.
Yeah.
And then discrete or continuous?
Just continuous for this one.
Oh, okay.
Yeah.
Oh, yeah.
Got it? Yeah.
Yeah.
Sick. I'm glad I remember where this stuff is without looking at it. But cool. So that's going to be our probability for our denominator, which seems quite low probability. Greater than 108. I mean, I guess that makes enough sense. It's over 2 standard deviations away. Because 95 plus 5 gets you, yeah, it's over 2 standard deviations away and pointing right. So, seems fair enough to be quite low. Anyway, now for the more complicated bit, which is the intersection of these two things. When you do these enough times, you'll be able to just look at it and know what's going on. But even myself nowadays, I'll pretty much just default to a number line. It doesn't take that much effort, and at least you'll walk away knowing that you're a bit more confident that you've got the right simplification of that intersection. So the values of interest here are 108 and 112, so we're just going to dot out each of those. Less than 112 just means going from here to here. Don't mind so much about whether you use a dark circle or a white circle. When it comes to continuous probability, they're effectively the same thing. There's no difference between inclusive or non-inclusive. And greater than 108 is going to do this. And so the intersection just means where do they overlap. So in other words, between 108 and 112. So this numerator now is actually probability 108 less than or equal to t less than 112. Again, you can chuck the equal signs on there if you really want, but it doesn't make a difference. Again, this is a probability over a range of outcomes, so the exact same CAS function is what we'll be using. I'll go through the setup wizard for it again, just because things have changed, although as you use it more and more, you'll start to recognize that you can actually just sort of plug in and replace the values in the syntax after the fact, rather than using this wizard. By the way, 108 was our lower bound, 112 was our upper, mean 95, standard deviation 5. We get our numerator. Two very, very small values. Does that also make sense? Being 108 to 112, yeah, again, we're pretty far right. And we're only going further right. So, this one was our numerator. The other one was our...
I got 4.3242.
Did it have, like, e to the minus something?
Yeah.
Yeah, so that just means it's not given it to you in the decimal form, it's given it to you in scientific notation. So you'll notice the numbers that you said, 4.32, are those leading digits. So you would have got e minus 3, I think?
Yeah.
Yeah, so that just means it starts at the third decimal place.
Oh, okay, cool.
I can have a look later on with the Casio, see if there's a way to remove scientific notation, because it'll be a bit better if, well, if you can just read straight off the decimals. But that's what that means.
Oh, okay.
Either way, if you have the E syntax there, I think you might need to put brackets around your number, because I think it treats E as a multiplication, because it's like 10 to the power of minus 3 there. So when you do your division, it might come out a bit weird, so maybe just go ahead and put brackets around each of those terms. And yeah, just make sure you do the division in the correct order. The numerator goes on top, so that was the 108 to 112 was our top bit, dividing by the bottom bit, which was just 108 to infinity. And as a bit of a sanity check, that is indeed a number between 0 and 1, and yeah, we should be fine with it. As far as rounding goes, let's have a look. What did it say? 3 decimal places, so we're looking at 0.928 as an answer for that one. If you really wanted to, you could... Nah. I was going to suggest that maybe you could do the fraction all in one go, but you're better off probably just doing it across two separate things. And maybe to be a bit safer, rather than grabbing these values, you can grab the actual like normal CDF syntax itself, and that'll also work. And that way it's a bit clearer which one's which, because if you look at these two numbers, just those two numbers, they're both basically 0.004, so it can be a bit confusing which one's which. Maybe consider grabbing the syntax itself. This works on the Casio as well. You just got to grab your pen and highlight and drag it in the same sort of way. But okay, that's that question. You use that approach for all conditional probability questions, whether or not it's continuous or otherwise. Always just set up the conditional probability formula, and then the only difference is going to be based on what area of study it is, will be what technique you use to solve those probabilities. Okay, part C. Manufacturer has determined that 81-ish% of the sensors fail between 90 and 105. A new improved version of the sensor will have a new mean and a same standard deviation. Find the values, okay, plural, of k, such that 81.86% of the new sensors now fail between 95 and 110. Cool, cool. Okay, so we've got two separate things going on there. It says find the value of k, which is a mean. That's the thing we're trying to solve. Does anyone have an idea on at least how you might go about starting this? The key thing to watch out for there is that we're trying to solve the mean.
I'm guessing formulas.
The formulas of what, sorry?
Standard deviation.
Yeah, that Z formula thing that has the standard deviation, the mean. Yes, that's the one we're going to be using. So, Z is equal to X take mean on standard deviation. This is the only equation within normal distribution. In fact, yeah, it's just flat out the only equation in normal distribution, I think, unless I'm forgetting one. It has the mean in it, so we should be... It seems like a good idea to use that equation. So, what does that mean for us? If we're trying to solve for this one, it means we need to either have all three of these solved, or two of those solved across two separate equations. Because we have two separate pieces of information, the whole 81.86 thing, and then like for 90 and 105 versus 95 and 110, it's, to me, leaning towards needing two separate equations. Good news is, across both of those, we saw that the standard deviation was supposed to be 5 in both cases, so we can go ahead and just leave standard deviation as 5 regardless. The mean is going to be k, just based off of the question. It does say find the values of k. I guess I should probably say mean 2 is going to be k, because mean 1 is still going to be the old mean of 95. So mean 2 is k, mean 1 is 95. Standard deviation 1 and 2 are 5. What else do we need? I guess x and z values. So we actually got 4 x's to work with. We got 2 for the first distribution and 2 for the second distribution. I guess because we care about the k thing, we're going to start with the distribution that has k in it. So let's take it from there. 81.86 is between 95 and 110. Okay. So if we think about distribution 2, I'm going to have that. I'm going to have the mean as k. And then from there... Now the interesting thing about this one is it doesn't necessarily imply that the probability is weighted both sides. So that's a bit concerning. We can't necessarily just say between here and here is 81.86. It could be the case that 95 is still up here and 110 is still... No, I guess it couldn't. At least not that close. You have to have it at least weighted on one side. So it could be equidistant, it could be pushed a little bit right, or it could be pushed a little bit left. Maybe that's a bit of a tough one to start with. We'll do distribution 1 instead. That one's a bit easier to work with because we know the mean is 95 and we know it's still 81.86 between 90 and 105. That is absolutely equidistant. Wait, never mind. It's not. It's actually weighted over. Sorry. 105 will put it at 2 standard deviations over there. This is only 1 standard deviation this way. So that's fine. This is 81.86, which means that 1 minus that has to be distributed outside of both of these areas here. Now, these are some x values. We want to get equivalent z values. Remember, ultimately we're trying to fill out everything that we can for this equation. And so we've got a couple of x's. So if we just pull this back down, z equals x minus the mean. Where is it? The mean was 95 over the standard deviation of 5. Is this going to be at all helpful? Not really, because it's not going to actually have k in it. And if I just choose any of these x's, I can get the equivalent z via inverse normal. Maybe we do have to rely on this approach here, but applying it to this. So we have a mean of k. We'll have temperatures of 95 and 110. 95, 110. We'll do the same thing here. 81 point, was it 96? 86. And then again the whole simultaneous. Okay, so if these are supposed to be equivalent, there is one thing that could potentially work here, which is if these
Are they supposed to be equivalent?
Yeah, I mean that's the thing, right? Like, are they supposed to be equivalent? We're trying to force a new mean fail with the same standard deviation.
So the z's would be the same then for the 2 different
Yeah,
sides is equivalent.
yeah. Like that's what I'm sort of thinking, which is like, basically, yes, the z's will be the same, but also there's also probably also a way to hack it, which is to say, well, okay, if we know that essentially everything's just being shifted right by 5, like if you look at all these, sorry, this is supposed to be 110, everything's being shifted right by 5, the new mean, at least one of the possible values, is going to be 100.
100, yeah.
But there's nothing in the question that explicitly says they're supposed to be the same, which is why I'm a bit worried and trying to approach other options. I guess we'll just go ahead with the assumption that they are equivalent.
Does that mean k is 100?
Well, one of the values, I'm assuming k would be 100, yeah, but it does say find the values, plural. And so what that likely means is, going back to what I mentioned earlier, which is because there's nothing explicitly stating that it's going to end up being the same between them, we could end up with, what would it be?
Or we could find Z1 and Z2 by doing 95 minus 100 divided by 5.
95.
And
Yeah,
then-
so if you already have the
and
k,
then-
yeah.
110 minus 100 divided by 5, and we get negative 1 and 2, then I'm not sure though, but we find the probability between negative 1 when x is greater than negative 1 and less than 2.
Yeah, so that's all valid. It is. We know that ahead of time because the standard deviation left is 1 left because it's standard deviation 5. Standard deviation is 2 to the right. That's also, remember, our goal is to solve for the values of k. Finding the probability, we already kind of know. It's more about trying to figure out how we're going to get the second option for k. Which means we need to still have a setup with this in here. And so how do we now do this? Net probability on either side. K being 100 is, yeah. K being 100 makes sense. I think the other thing is it could also be weighted on this side as well, because the symmetry is not necessarily between the two distributions, but rather the fact that it's 1 standard deviation left, 2 to the right, is the same thing as 1 to the right, 2 to the left. And so what's the equivalent there? Well, if this was 100, then all you're literally doing is shifting it over 1 more. So 105.
Oh yeah.
100, 105. That would get you 2 left, 1 right, should also be the same probability as 2 right, 1 left. I think that'll do it. It was a good question, God. Let me double check that. So I got the answers that I can pull up. Just hold on. What did they say? I'll even change the screen share over so we can all read it together. Okay, so it's right here. Standard deviation is the same, intervals move 5 to the right. Okay, yeah, it's the exact same. Nice. They didn't really talk too much about where the 105 came from. They just kind of said symmetry, but that's going to be the, well, the explanation I gave earlier seems about right for that. That was a fun one to explore. Normal distribution tends to, I think this was the second time a normal distribution question has been quite weird with the Z equation stuff. There's been a few like that, which is nice. They're good questions to practice. But okay, have I pulled that screen share back? I have. Awesome. That was a tougher one. Does anyone have any further things that I need to clarify based off of that question?
So,
No.
sorry.
Yeah, go for it.
So does this mean every time we do a normal distribution question, we have to like verify symmetry?
Oh yes,
Like
normal distribution loves symmetry. You pretty much always are working with some sort of symmetry going on with it. Even something just as simple as flipping your probabilities from left to right. And like the other thing I was considering was maybe there's a way to say, well, okay, if this is 81%, then you split 81% somehow between both. But because it wasn't equidistant, we couldn't really do that. But all these things are relying on the fact that normal distribution is symmetrical about the mean. They'll pretty much always play with that. Yeah, good observation. Okay, we did C, on to D. Laboratory test, another sensor. 98% of a random sample of sensors continued working at a temperature of 80 degrees and 4% continued working at 110 degrees. Determine the estimates for the values of the mean and the standard deviation. Okay. Yeah. 98% of a random sample of sensors. We don't know how big this random sample is, so we can't really call this sampling an estimation because we kind of need our N and P's. We can get a P, in fact they're just given to us, but we don't actually have an N, which means we're still working within normal distribution. Okay. So if we're still working within normal distribution, then let's draw up what we know. We know 98% in a given sample continued working at a temperature of 80, which means is it because they're in a sample that we handle it differently? 98% of a random sample continued working at a temperature of 80 degrees. No, I think it's just the same. You put 80, and that means 98 on that side. Then, so this can be like sample 1, for instance. Sample 2. Wait, no, it's the same thing. 98% of a random sample continued working at a temperature of 80, and 4% continued working at 110. Yeah, no, it's on the same distribution. There's no 2 samples. I misread that. So that was 110. That should be way over here because everything right of that should be 4%. Cool. Okay. Determine estimates for the values of the mean and standard deviation. Again, we are solving for mean and standard deviation. This time, I don't think it should be as tricky, just based on the fact that we've only got one distribution that we're looking at. So let's have a look. It's obviously going to be Z equation related because we're trying to find mean and standard deviation, and because we're trying to find two things highly likely to be a simultaneous. So, what do we have so far? Well, we have an unknown mean, we have an unknown standard deviation, we have two separate x values, one with 80 and one with 110. What we don't have is the equivalent z's that go along with that. In this case, finding those z's is going to be significantly easier. Can anyone suggest how we would find those z's? Z being the standard normal equivalent. Also, to make this a bit clearer, I'm going to redraw this arrow so it's pointing all the way right. It's not between 110. The good thing about the Z, the standard normal, is that you know for a fact the mean is 0 and the standard deviation is 1 for Z specifically. How do we get equivalent Z values for these X's? It was suggested already in the previous question. And while it wasn't super necessary for the previous one, it will be necessary for this one. This is where inverse normal comes into play again. So if you look at even just the default values of inverse normal, they are pre-populated with a mean of 0 and a standard deviation of 1. I think that's also true for the Casio. I'm not entirely sure. But at least for the TI Inspire, it's pre-populated with mean 0, standard deviation of 1. If you use a mean of 0 and a standard deviation of 1 and pop in the relevant probability, you will get the equivalent Z for that thing. For TI users, we have to make sure it's pointing left. For Casio users, you just need to make sure that you change your tail setting to right, and then you can absolutely plug in 0.98 and 0.04 for each of those equivalent Zs. For us, we got to flip them, or at least for myself, I've got to flip it. So rather than putting 98%, I've got to put 2%, because the TI Inspire will always default to whatever's pointing left. Then again, for the other one, if it was 4% pointing right, then that means 96% pointing left. And that gets us our two Zs to go along with our X's. From here, we have two equations, two unknowns, simultaneously solve. Yeah, why not? X and Y can be used. Maybe not X and Y just because X is already there. Let's just go with A and B. Okay, so Z number, so this one went for the 2%, which is the equivalent for 80. So let's go ahead and do that. 80 minus, I'm going to say the mean is A and the standard deviation is B. And then same thing for the other equation. Control V, and that one had 110 minus the mean divided by the standard deviation. And then hopefully what we get makes a decent amount of sense. We're expecting a mean of 90-ish and a standard deviation of 5-ish. The standard deviation of 5-ish makes sense because it's very close to the standard deviation that we started with. And the mean of 90, I mean, not too close, but you know, the fact that the standard deviation is pretty close makes enough sense. And you can even also at least plug in the value of the mean that you got here, and at the very least you would expect it to be somewhere in the middle between these two, which it is. Any questions there? So these were the actual values. Just make sure you remember which one's A and which one's B. Rounding, of course, to 1 decimal place, giving us 90.8 and 5.2.
For the first part, inverse norm.
Yeah.
How do I do it on my CAS? I don't know. I couldn't find it. Do you mean inverse CDF or?
Yeah, I think yours says inverse norm CDF. You would have done it at the very first question, 2A. Whatever you did there.
Oh, yeah.
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 Again, as I mentioned, if you're going to use my numbers here, just make sure you do a left tail. Alternatively, if you wanted to use the ones that were in the question and in the diagram, just make sure you use a right tail option. If you have any trouble with that, just interrupt me. I will mention the next question, but yeah, feel free to interrupt me as I'm talking. No offense at all. Another manufacturer of sensors claims that 10% of their sensors will continue working at 110 degrees. Assuming the claim is true, find probability that in a box of 20, at least 2 of them will continue working at 110. So, these indents, they don't always use them in SACs and exams, but they are kind of nice because when they are there, the likelihood that the probability type has changed to a different area of study is quite high. Haha, probability changing. And so definitely worth paying attention to the next bit of wording in the question. Has the probability type changed here?
Yeah, it's a binomial.
Binomial, yeah. Why do you think that?
Because it says, I don't know, but the wording felt like it.
Yeah, felt like it. So you probably saw a box of 20 sensors and you're like, cool, that's my N. And the other thing about binomial is that you need 2 outcomes. In this case, it's working or not. Right? Does the sensor work? Did it fail? The other thing is, I guess it's discrete, right? You know, you got a discrete number of sensors, at least 2 of them. It's a physical number of sensors. It's in the discrete section, specifically the binomial section. Well done. So, now that we know it's binomial, let's write out the probability statement that we're trying to solve. So, it says probability of at least 2 of them will continue working. So, in other words, probability x greater than or equal to 2. Because remember, binomial is all about successes or fails. It doesn't really give a shit that we said 110 degrees or whatever. That will still matter, because with binomial, we need n, we need p, and we need x. We've just done x. X is that range of outcomes greater than or equal to 2. N is 20, so that was just given to us. It's a number of items that we have. What we don't have yet is p. How might we go about finding it?
10%?
Oh yeah, it does
10%.
actually say it right there. Yeah, that's right, in the indent. 10% of sensors will continue working at 110. Yeah, no, that's perfectly right. I kind of forgot about that. I thought we might be doing a normal distribution to solve it. But yeah, it absolutely does say 10%. Awesome. P is 10%. This is everything we need. So, back to our CAS. This will be the binomial CDF now. which again for Casio should be in the distribution section, near enough the normal options. You also have the binomial options. Again, CDF, if we have a look, we need number of trials, probability of success, lower and upper, of which we have all of those. It was x greater than or equal to 2, which means, well, it means 2 to 20. N was, get out of there, there we go, 20, and probability of success, 0.1. Again, on the Casio, the things are just going to be slightly out of order, or different ordered. It's still the same exact things though. Let me know if you have anything that looks a bit crazier. And that's going to get us our answer. 3 decimal places, of course, just do the rounding there. What's that? Yeah, just 608. Cool. And then actually no, that is not the last question. F has another indent afterwards. Okay. F. Find the minimum number of sensors that should be packed into the box to ensure that the probability that at least one sensor will continue working is at least 90%. The wording on these is strange, but because they're so strange, it's recognizable. Does anyone remember, does anyone feel like they've seen that question before and maybe have an idea how we go about it?
Is this the guessing one?
Yeah, this is the one that I do a guess and check on. Again, let's see, at least one, because it's a range of outcomes, we determined that doing the inverse binomial inverse binomial didn't really help. It only ever helped if it was like x equals something. And while you could absolutely create an equation for this, it's not great. Would you happen to know where I can find this question in the Jacaranda textbook? I could, yeah. I'll follow that up later. I'll grab because I got a copy of the Jacaranda as well. Okay. Where were we? Yeah, so you could create an equation to try and solve this. It's not overly pleasant. I'll show you just briefly what that would look like if we have a look at... Actually, where is this? This will be in binomial. That's what it'll end up looking like. In fact, it's probably this will be the exact working out, since it's once again x greater than or equal to 2. Actually, maybe is it still x greater than or equal to 2? No, at least 1, so it'll be greater than or equal to 1. But same idea, where you basically have to manually open up each of those Bernoulli sequences in that sequence, set up your equation, cas solve, kill one of the values, and then round it properly. Alternatively, you could just go ahead and guess and check your way through. First, we need to know what the actual parameters are, though. So, let's go ahead and do that. What are we actually aiming at? So, we wanted at least one sensor will continue working. So, probability x greater than or equal to 1. And we want that to be 90% likely. Cool. We don't know the n. The p has remained the same. So my suggestion is that we just basically guess and check our way through it. Let's just start with 20 just because whatever, it was used before, so let's start there. Greater than or equal to 1, and then whatever you chose as your n for your initial guess, you're going to choose as your upper bound. We hit the button. Did we hit 90? We did not. So we will increase our n and our upper bound. Did we hit 90? Yes. We should now decrease it a little bit. And we are going to fine tune our guess and check until we get the breakpoint. That is very likely the breakpoint, but just to be safe, let's try n equals 21 as well. Cool, so 21 did not reach it, 22 is the first time that it hits 90%. The answer is going to be n is 22. Yeah, much faster than setting up the equations. There's never any show you're working for this sort of thing. If there is, it'll be in the tech active section, and all you have to do is print off my notes on this, and you can be like, well, okay, at the very least I can try and copy down some of this stuff. But I would be shocked if they wanted you to show working for this sort of thing. any questions as to how that guess and check works? Typically it's going to be the case that as you increase n, your probabilities go up. As you decrease it, it'll go down. Yeah, that's the only thing probably watch out for. Like, how do I hone in on the value? Okay, next up. To test this company's claim, a random sample of sensors was tested and an approximate 95% confidence interval is found to be that. Find p hat. Hopefully a dead giveaway. What area of probability is this talking about?
Proportion.
Proportions, yeah. P hat, dead giveaway. Approximate confidence interval, also another dead giveaway. This here is probably the easiest question as far as computing the answer, or just finding the answer. Finding p hat given an interval. Does anyone remember how we find p hat if we know the interval? It's easy to calculate, not necessarily easy to remember. This has a surprisingly low rate to remember how to handle. Before I go straight to the answer, that's what the confidence interval looks like. It's p hat minus a certain number of standard deviations, p hat plus a certain number of standard deviations. We're trying to get the p hat. So assuming that it's p hat minus, p hat plus, we want just p hat. No worries. So again, this is it's kind of similar to how we treat the symmetry in the normal distribution. Because it's p hat plus and p hat minus on both sides, whatever the middle is just p hat. So you're just doing a midpoint on this. That's all it is. So if you have your interval, just do the midpoint of that interval, whatever that comes out to be. So let's do exactly that. As I said, very easy to calculate, but surprisingly hard to remember what you do. Plus 1414 divided by 2, p hat acquired. Awesome. H is the harder one. Find the size of the sample, so finding n. So, again, if we have a look back at, well, that almost gave it away, but I didn't give you enough time to read it. If we have a look at our equation for calculating the confidence interval, it's z, it's p hat, it's n. Those are all the things that we care about. P hat we just found, n is what we want, z. What is z? By default, for 95% confidence interval, you give z equals 1.96. Let me just see if they chose anything different. They did not. Okay, so unless they tell you z equals this, use z equals 1.96 for the 95% confidence interval. In tech-free, that's when they'll typically say, hey, just let z equal 2. We'll make life a little bit easier for you. But okay, so all I'm trying to highlight here is that we know z is 1.96. We know p hat 0.08. N is the only unknown in the interval, and we have our lower and upper bound. How might we go about solving for that n? It's a bit weird because we've got an interval full of information rather than an equation. So, you actually have a choice here. If you know the interval, you know that this one was created by doing the p hat plus some number of standard deviations, and this one was created by doing p hat minus some number of standard deviations. We know the p hat, we know the z is 1.96, and we know either the upper or the lower, depending on where you want to use. So, if we know our upper bound, for instance, is 0.14, then we would be putting 0.14 as the thing we equal to 0.08, which, funny enough, is actually the exact same p hat that we have, plus the z, if we're using the upper bound. If we're using the lower bound, we do the minus version instead. Everything else from there is the same, and you just cas solve from there. Both of those will give you the exact same n value. So you have a bit of a choice there, basically. You can use upper or lower. And yeah, just to finish it off, let's do one of them. So let's say we do the lower bound, 0.0186 is therefore equal to p hat, so 0.08. It's lower bound, so it's minus that number of standard deviations, 1.96 times the square root of, I forget what goes in there, what is it? P hat 1 minus p hat on n. Cool. 0.08 times 1 minus 0.08 over n. I'm just going to use x. And then we're just going to have to round that to 75. Because it does say getting to the nearest whole number. Any questions? Maybe just for the fun of it, I'll also show you what you do, what you get if you were to do the upper bound. All you would have to do is change that minus to a plus and update this value, which would now go to 1414. You can see both roads lead to Rome. Awesome. Okay, I guess we'll wrap it up with the Jacaranda textbook question. So let me find that. Textbooks, Jacaranda, 3-4. Oh yeah, if anyone wants it, I'll just chuck it in the chat right now. Okay. Where are we at? Normal distribution. Hang on, sorry, what was the question again? It was, this kind of question was the guess and check thing. So that's in binomial. 10 dot something or other. We're looking at 578. Okay. Where do they do these questions? Probably starting here in 10.3. Yeah, okay. Sure. Yeah. So here's 1 in 22. So you can see you got a p-value, how many games, you know, find n. Find n, number of tickets. Is that it? Surely that's not all the ones they're going to give you. Oh well, I mean, you got the Cambridge as well, I guess, which will have a heap to practice. They've got a whole chapter section dedicated to it, which I will just show now for reference. Where is it? 14C, finding the sample size. So, if you can do all of these, you'll be pretty good at this. So I've got both the Cambridge and Jacaranda up for download. Oh, what am I? Type of question incorporating everything in statistics. Incorporating everything, as in like the stuff we did with the Z equation? Oh, okay. I mean, that should just be anything normal distribution related. Let me find where that is. probably starting 12.4. That's when inverse normal starts playing into the case, into the chapter section, and you absolutely need inverse normal to get your Zs. So that will be the place I'd have a look. I'll keep having a look. We've hit time now, so I just want to say thanks everyone for coming. If you guys want to stick around to see where you can practice this stuff in the Jacaranda, feel free. And if you have any questions as well for me, I'm also open to
Thank you.
answer. Yeah, no worries. Take care.
For the PDF you were using before,
Mhm.
do we have access to that?
Yeah, you should have access to all of these. They should be in the class modules section. Yeah, in fact, you're live now. Are you able to log into the school?
Yeah.
Yeah. So just have a look in the classroom section. You should see those are all available to you.
Okay.
Just let me know if that's the case. Because yeah, you'll then want to go to the probability section, and you'll see all those relevant there.
Oh, okay. Thank you.
You found them? Yep.
Mhm.
Awesome. All right. Have a good day. And also make sure you send me your availability for private class. I'll need to organize a tutor that meets your availability, and then you can have your private class before the Friday.
Okay, sure.
Awesome. I'll leave you to it then.
Did you send me the link?
Link for...
The availability, or do I
No, I
just...
was asking for your availability. Oh, you wanted me to
Where
send you
do
a
I-
timetable. I just wanted you to like let me know, like, is there anything that's stopping you from, like, I don't know, having a class tomorrow or the next day?
No.
Nothing? Okay, cool. So, sorry. Okay, so I'll have a look through through our tutors. We'll find one. Maybe not tomorrow specifically, because it'll be a bit fast turnaround time. I'll try, but we could probably do a Thursday, and that might even be better. So you're doing it right before the SAC. Okay.
Okay, sure.
Awesome. All right, I'll get on that, and I'll yeah, you'll receive a message from one of our tutors, and we'll organise the class.
Okay, thank you.
Have a good
Bye.
night.